All right, let's get right into it. Today, we're basically going on a mathematical detective mission. We're going to deconstruct one of the most famous and maybe one of the most intimidating numbers in the entire history of AI. Yeah, we're cracking open the blueprint of GPT-3. 175 billion. I mean, just look at that. It's not just a number, right? It was a statement. When this dropped back in 2020, it was this massive, monumental leap in scale that pretty much changed everything. It really kicked off the whole generative AI race that we're all living in today. But you have to wonder, where did a number like that even come from? Was it just some big, round number they picked for a press release? Something that sounds good? Or is there an actual, precise blueprint behind it that adds up to exactly 175 billion? Well, that's the mystery we're going to solve right now. Okay, so our investigation begins. And here's the most important thing to get your head around. This number isn't just one big thing. Nope, it's actually the sum of a bunch of smaller, very carefully designed parts. And we're going to tally them all up, piece by piece. So here's our game plan. We can basically break the whole model down into three main sections. You've got the input part, then this huge transformer stack in the middle, that's the real powerhouse, and finally, the output. And hey, as we go, keep an eye on that parameter accumulator on the side. We're going to watch it fill up as we get closer and closer to that 175 billion goal. Okay, before we start crunching the numbers, these are the key ingredients for our recipe, pulled straight from the original paper. You'll see some important specs here, like the 96 transformer layers. You can think of that as how deep the model's thinking goes. And then there's the hidden dimension of 12,288. That's all about how rich its understanding is. These numbers right here, they're the engine for everything we're about to calculate. All right, first piece of the puzzle, a model like this can't actually understand words like cat or dog. So the first thing it has to do is turn them into numbers, into vectors. That's the embedding layer's job. The math is pretty straightforward. You take its vocabulary size, about 50,000 words, and multiply it by that embedding dimension. And bam, that gives us our first chunk, 614 million parameters. So about 0.6 billion. And if you look at our accumulator, there we go. Our first little block is filled in. We're on our way. Okay, first piece is on the board. But honestly, that was just the appetizer. Now we're diving into the absolute heart of this machine, the core engine. This is where the vast, vast majority of those 175 billion parameters are hiding. So what is this engine? Well, it's a stack of 96 identical transformer layers. The best way to picture it is like a skyscraper with 96 floors. And on every single one of those floors, there are two main rooms that hold pretty much all the parameters. One is the multi-head self-attention mechanism, and the other is the feed-forward network. So let's check out that first room, self-attention. This is basically how the model figures out which words in a sentence are most important to pay attention to. And to do that, it uses four really big matrices. As you can see from the math, each one is a huge 12,288 by 12,288 grid. That adds up to about 604 million parameters. And remember, that's for just one single layer of our 96-story skyscraper. Okay, now for the second room on each floor, and this one's even bigger. It's the feed-forward network. What it does is kind of cool. It takes the information, blows it up to 4 times its original size to think about it, and then shrinks it back down. This whole expansion and contraction thing needs 2 massive matrices, which gives us another 1.2 billion parameters. So you add that to the attention part, and you get a grand total of about 1.8 billion parameters for just one layer. One floor. So we now know how big one floor of our skyscraper is. Now it's time for the big reveal. This is where it gets crazy. Let's see what happens when we stack all 96 of those floors on top of each other. And this right here is where that mind-boggling scale comes from. We take the 1.8 billion parameters from one layer, we multiply it by 96, and suddenly we're at a staggering 172.8 billion parameters. I mean, just look at our accumulator bar now. It's shot all the way to the top. This is it. This is the absolute core of GPT-3. So the mystery is pretty much solved. We just have to put the final pieces together. We take that massive 172.8 billion from the transformer stack, we add the 0.6 billion from the embedding layer at the very beginning, and then we throw in a few other minor bits and pieces, and there you have it. The grand total lands right at our target, 175 billion parameters. So no, it wasn't a marketing gimmick, it was pure math. Okay, so that answers the how they got the number. But that's only half the story, isn't it? The more interesting question is why? Why 175 billion specifically? Why not 50 billion or 500 billion? This is where we have to get inside the heads of the architects. Yeah, this decision wasn't random at all, not even close. It was all guided by this incredible research from OpenAI on something they called scaling laws. They basically discovered what's almost like a law of physics for AI. As you make a model bigger, add more data, more parameters, its performance just gets predictably better. The philosophy was really simple. Bigger is actually better. So the obvious next question is, why stop there? Why was 175 billion the magic number? Because back in 2020, that was the absolute engineering sweet spot. It was this perfect balance point between the ambition of those scaling laws, the reality of the hardware they had access to, these massive GPU clusters, and just the practical economics of it all, the time and the money. Going any bigger would have meant insane costs for maybe just tiny little improvements. To make all these numbers feel a bit less abstract, let's use an analogy. Let's think of this whole thing as a digital brain. Those 175 billion parameters, they're like the synapses, the connections that hold all the knowledge. The 96 layers we talked about, that's the depth of its thought. And that big 12,288 number for the dimensions, that's the richness and nuance it can understand for any single idea. So, what was the payoff? What was the legacy of building this massive digital brain at a scale nobody had ever seen before? What did it actually do? Well, the payoff wasn't just getting a bigger number to put in a research paper. Something incredible happened. It unlocked a phenomenon called emergence. Once it hit that 175 billion parameter scale, it suddenly developed a new skill. It became what's called a few-shot learner. This meant you could show it just a couple of examples of a task it had never been trained on, and it could just do it. And what kind of abilities are we talking about here? We're talking about things like writing entire, coherent articles from a simple prompt, translating languages on the fly, even showing glimmers of logical reasoning. And the craziest part is, nobody programmed these skills into it. They just appeared as the direct result of its sheer size. And that really brings us to our final thought for today. GPT-3's 175 billion parameter scale was a massive milestone back in 2020. It unlocked abilities that honestly felt like science fiction. So it really makes you think, doesn't it? With the models we have today reportedly crossing into the trillions of parameters, what new emergent abilities are being unlocked right now as we speak?